Welcome to the deep dive. So our sources today are tackling one of the most frustrating and persistent challenges in AI scale-up.
Right.
How do you get truly general, powerful reasoning in LLMs without, creating an inherent performance ceiling? For years, the gold standard has been supervised fine-tuning SFT on these meticulous, human-annotated reasoning traces.
Usually chain of thought or continuity. And that reliance on human examples is, well, it's a major liability.
Yeah.
It creates two fundamental bottlenecks.
Okay.
First, it basically caps the model's performance at whatever the best human examples are. It stops the model from finding potentially superior, maybe non-human ways of reasoning.
And the second is just cost and scale, I assume.
Exactly. It creates this huge scalability problem because annotating high-quality CAT data is just incredibly resource-intensive, and that's the core innovation we're diving into today.
DeepSeek-AI's work on DeepSeek-R1.
Precisely. It's this definitive demonstration that you can achieve advanced, even emergent reasoning abilities purely through reinforcement learning, just RL.
Completely bypassing that need for human-labeled SFT data.
Completely.
That is a game changer if it holds up. So our mission today is to give a really comprehensive professional overview of how they pulled this off. We need to detail the DeepSeek-R1 architecture, starting with the pure RL model, R10.
And then the multi-stage pipeline that gets us to the final R1 model.
Exactly. Then we'll analyze the key performance results, especially on these verifiable tasks like advanced math, coding, and, graduate-level STEM. Okay, let's unpack this, starting with the foundation, DeepSeek-R10.
So the whole premise behind R10 is pretty straightforward. The idea is that restricting a model to just copy human thought processes inherently caps its potential.
Right, you're limiting its search space.
You are. If the base model has this latent capacity for, deeper problem solving, the training has to give it the freedom to use it. And DeepSeek R10 was built on a really formidable foundation, the DeepSeek V3 base model.
And that's a massive model.
It is. We're talking 671 billion total parameters, with 37 billion activated at any one time through a mixture of experts or MOE architecture.
So to leverage that scale for pure exploration, they needed a specialized RL algorithm. They didn't go with PPO, which is common, but with something called Group Relative Policy Optimization, or GRPO. Why was that the right choice here?
GRPO, which was introduced by Xiao and his team, was picked specifically for its efficiency and stability, especially when you're dealing with huge models and these really long action sequences.
With thousands of tokens in a chain of thought.
Exactly. The standard approach, PPO, requires you to train a whole separate and computationally very expensive value model, and you have to use generalized advantage estimation, or GAE.
Which is the method used to reduce the variance of the policy gradient updates.
Precisely. And PPO is great, but training that value model and getting GAE right becomes incredibly difficult, especially here where the model might generate thousands of tokens, but the reward signal only comes right at the very end.
It's a sparse and delayed signal.
Very. So if your value model is even slightly off, your training can just stall or even diverge.
So how does GRPO get around that computational nightmare?
It just completely gets rid of the value model. So instead of calculating the advantage based on some absolute baseline, which is what the value function gives you, GRPO estimates it using group normalized rewards.
Okay, what does that mean in practice?
Think of it this way. In a small batch, the model generates, say, G different potential solutions. Each one gets its own final binary reward. GRPO then judges an individual output relative to the mean and standard deviation of the other outputs in that same group.
I see. So it's rewarding outputs that are just better than the immediate average.
Exactly. Makes the calculation local and relative, which dramatically speeds up training and keeps things stable for these giant MOE models.
The reward design for R10 is just as radical in its simplicity. They used a rule-based reward signal, R-rule, based solely on the final answer being correct.
Yes, they weren't trying to reward a human-like process at all. They were just rewarding the verifiable outcome.
So what did that structure look like?
The reward is basically R rule equals RAC plus R format. RAC is a strict binary signal. Did the final answer for the math problem match? Did the code compile and pass?
And R format?
That's just structural. It just makes sure the model put its thinking inside the required think tags. But the crucial part is that there's zero constraint, penalty, or reward applied to the reasoning inside those tags.
And their decision to completely avoid neural reward models in this R10 stage, that's pretty telling, isn't it?
Oh, it speaks volumes about the challenges of scaling RL. That decision came directly from seeing how susceptible neural reward models are to reward hacking during large-scale training.
The model just learns to game the reward model.
Exactly. Even an outcome-based neural model can be gamed. By relying on these objective, rule-based verifiers, like a compiler or a strict numerical match, they stop the policy model from finding shortcuts that just maximize the score without actually solving the problem. The ground truth is the only authority.
Okay, let's shift to the results of this pure RL approach, because the performance trajectory of R10 is, well, it's truly dramatic. We're not talking about small gains here.
No, not at all.
On the AME 2024 math competition benchmark, the pass at 1 accuracy jumped from a base of about 15.6%, which is basically guessing, to an incredibly robust 77.9%.
And that's just the start. When they used self-consistency decoding, where the model generates multiple solutions and picks the most common one, R10 hit 86.7% accuracy.
That's better than the average human competitor.
It surpasses the average performance of all human competitors in that AIM competition, yes.
Yeah.
And we saw similar groundbreaking successes in coding competitions like Code Forces and in graduate-level STEM problems.
So it proves the hypothesis. The pre-trained model had this huge, unrealized reasoning potential that SFT just couldn't unlock.
It was latent, waiting for the right incentive structure.
So this capability wasn't engineered, it was self-evolution during the RL process itself. What stands out to you about how it learned?
The most fascinating metric for me is the sustained increase in the model's average response length. It's like its own internal thinking time just kept growing throughout training.
And it learned to do that on its own.
Completely autonomously. It learned that to maximize its chances of getting that final binary reward, it needed to generate hundreds, sometimes thousands, of tokens just exploring, verifying, and refining its strategies. This expansive CoT was entirely emergent.
It wasn't told to think longer. It discovered thinking longer gets a better result.
Precisely.
And this self-driven thinking time led to some incredibly sophisticated behaviors, things we usually associate with, well, human introspection.
Absolutely. The model started to show these structural components of reflective reasoning, of systematically exploring different solutions and doing these stringent self-verification checks. It wasn't just doing one calculation, it was generating multiple paths and actively looking for inconsistencies.
The aha moment example in the paper is probably the clearest window into this. It's almost startling to read.
It's a phenomenal example of emergent introspection. You see the model's chain of thought, and it starts down one path, but then suddenly it flags a realization by just using the word wait over and over.
Right, like a person pausing mid-sentence. Wait, that's an aha moment I could flag here.
And that shows the model autonomously learning and deploying these distinct reflective reasoning patterns based purely on optimizing for that final binary reward. It's an internal mechanism that mimics recognizing an error or finding a better approach without ever being shown a human doing that.
It just underscores the power of a clean, objective incentive. You give it that reliable ground truth reward, and the model evolves its own superior strategies.
It moves far beyond just imitating a human template. It's generating optimal reasoning paths, not just mimetic ones.
Now, despite R10's incredible raw reasoning, it wasn't a perfect product. It had some practical drawbacks that led to the full DeepSeek-R1 multi-stage pipeline. What were the main limitations from a user's perspective?
The two big ones were poor readability. The reasoning chains were often just incredibly dense, hard for a human to follow, and significantly persistent language mixing.
Because the base model was multilingual.
Exactly. So the chain of thought would frequently mix English and Chinese within a single response, which is a major user experience flaw.
So the goal of the full DeepSeek-R1 pipeline was to keep the powerful reasoning of R10, but fix these usability issues. How did they structure that multi-stage approach?
They used a four-phase strategy. It started with a small, what they called a cold start SFT stage, Dev 1. This used a minimal amount of human-aligned code data just to improve the user experience.
Things like using I instead of we.
Exactly. It was alignment-focused, not reasoning-focused.
Then came the first big RL stage, Dev 2.
Yes, and this is where they built on R10, but with a critical addition. In Dev 2, they integrated a specific language consistency reward, R language, alongside the rule-based R rule.
And how did that work?
R language is just calculated as the proportion of the target language's words in the CoT. This mechanism successfully stopped the language mixing, essentially penalizing the model for switching languages mid-thought.
So it forced it towards cleaner, monolingual output.
It did, though, with a slight but measured trade-off in raw reasoning performance. But it was worth it for the usability gain.
And after that, there's a second SFT phase, Dev 3, before the final RL stage. What was the point of Dev 3?
Dev 3 was crucial for making the model a generalist. It incorporated high-quality reasoning data from R10, but critically, it also introduced huge non-reasoning datasets. This boosted general skills like creative writing or open domain Q&A, where you can't have rule-based rewards.
Okay, so that brought it up to par as a general-purpose LLM. And in that final RL stage, they finally did bring in model-based rewards, but with a lot of precision.
Absolute precision. They needed model-based rewards for the general alignment targets, helpfulness, and safety. So they introduced a helpful reward model and a safety reward model.
And how did they keep those from interfering with the reasoning?
The helpful reward model was trained on about 66,000 non-reasoning preference pairs. And it was designed to focus exclusively on evaluating the utility of the final summary given to the user.
I see. So it doesn't pollute the core reasoning process.
Exactly. The final word structure is additive. R reward equals R reasoning plus R general plus R language. The high-stakes reasoning part stays anchored to the reliable rule-based verifiers, while general alignment uses the model-based rewards. It's a beautifully segmented reward function.
So putting it all together, what does the final DeepSeek-R1 actually achieve on the benchmarks?
It sets new high watermarks, especially in tasks that need deep reasoning. We're looking at 79.8% pass at 1 on AIM 2024, 97.3% on Math 500, and a really impressive 96.3 percentile on the Codeforces benchmark.
And compared to the original DeepSeek V3?
The gains are substantial, particularly on those composite reasoning and STEM benchmarks like MMLU Pro and Live Code Bench. This is a model that has genuinely internalized problem solving.
Let's talk about a behavior that shows intelligence beyond just a score. Adaptive test time compute scaling. R1 doesn't just learn to think long. It learns to think as long as it needs to.
This is a hallmark of emergent intelligence from RL. During inference, DeepSeek-R1 dynamically allocates its computational resources, its thinking tokens, based on how complex it thinks the query is. Simple tasks get solved quickly, maybe using fewer than 7,000 tokens.
But for the really hard problem.
For the really hard ones, right at the edge of its capability, the model can automatically trigger the generation of over 18,000 thinking tokens.
That is a massive internal resource allocation.
It is. It demonstrates a learned capacity for metacognition. The model has internalized a way to scale its computation proportional to difficulty, all without any human instruction.
And if you contrast that with how non-reasoning models try to scale, the difference is pretty stark.
Oh, absolutely. Non-reasoning models, like recent GPT-4o versions, often just rely on majority voting. They generate, say, 16 independent samples and vote on the answer.
But that's not very efficient.
It's extremely token inefficient. And crucially, it fails to close the performance gap on hard math. Why? Because those independent samples can't backtrack or self-correct errors midway through. R1's internal adaptive reasoning chain is doing all of that automatically.
So R1 is scaling the quality of its thought, while majority voting is just scaling the quantity of its attempts.
That's a perfect way to put it.
Okay, finally, let's touch on knowledge transfer. This is key for democratizing this kind of capability. Were these emergent reasoning patterns transferable to smaller models?
Yes, and this is maybe the most economically significant finding. DeepSeek successfully distilled R1's reasoning capacity into much smaller base models, specifically a Qwen32B model, by using SFT on the high-quality reasoning traces that R1 generated.
And the performance difference compared to models that tried to learn this directly through heavy RL is staggering.
It really is. It proves that distillation is the future here. The distilled model, DeepSeek-R1 Distill Qwen32B, got 72.6% pass at 1 on AIME. Now, compare that to a similar model, Qwen 2.532B0, which went through large-scale RL directly. It only got 47.0%.
Wow, so the complex strategies unlocked by the biggest models are highly transferable.
Well, highly. It makes distillation a much more economical and effective path for smaller models than trying to repeat that heavy, expensive RL process from scratch.
So if we synthesize the core contributions here, the DeepSeek-R1 project has fundamentally shifted the narrative around reasoning in LLMs. What's the single biggest breakthrough?
The breakthrough is the definitive proof. Pure, outcome-based RL, when you back it with reliable, rule-based verifiers, can unlock this profound, sophisticated reasoning, potential reflection, verification, adaptive compute that's already inherent in large base models. It frees us from the performance ceiling of human-annotated data.
But the paper is also upfront about the limitations. This method isn't a silver bullet for everything yet.
Correct. R1 still has some practical alignment issues, like suboptimal tool use, and it can sometimes overthink simple questions, which is inefficient. It's also sensitive to few-shot prompting. But the biggest challenge is still that dependency on a reliable reward signal.
The whole success hinges on having objective, rule-based verifiers for math and code.
Exactly. Scaling this pure RL approach to subjective tasks, things that lack those verifiers, like open-ended writing or nuanced dialogue, that remains profoundly difficult. You run right back into the problem of reward hacking as soon as you have to rely on neural reward models.
And that leaves us with a provocative thought for you to consider. Given that machines with these advanced RL techniques are now poised to decisively surpass human capabilities in any complex task that is objectively verifiable, we have to ask this.
What's next?
How should future research prioritize defining and refining robust reward structures for all those complex subjective problems where objective verification is inherently impossible? The path to AGI runs directly through the reward function, and right now that path is blocked by subjectivity.
The objective verification barrier is the next great frontier.
Thank you for joining us for this deep dive. We'll catch you next time.